So yeah, this is I'm just going to describe some ongoing work on a particular kind of quantum code that's hasn't been studied so much. It's been around for quite a while as an idea using permutation invariant subspaces of qubits to encode information. But recently it's gotten a lot of more attention for actual useful applications. Particularly with keeping in mind actual physical constraints of systems that would make use of quantum error correction. So just going to give an extremely brief primer on quantum error correction, just sort of on the same page. And then an introduction to permutation invariant there's several different types of them. I'm just going to focus on a couple types as examples. And then I'll talk about how you can use these for designer gates. That is, you can sort of design the code so that it can be transversal for the type of gates you want. And then I'll mainly be focusing on applications for gates for quantum computing, in particular non-Clifford gates. And then also using these codes for quantum sensing with the idea that you'd want to make use of entanglement to enhance the precision of your sensor. And so you'd want to be able to also protect against errors. So you'd want to be able to do some error correction. And then I'll talk about some ways you could do some actual encoding and decoding of these states using physically realistic operations. All right, so we're all aware that quantum computing is great, but it's hard. We have noisy gates, and we just have noisy environments. And these can all be thought of as the environments becoming entangled with our computational register. So the philosophy of quantum error correction is to fight entanglement with entanglement. And this field has been going for quite some time now, really since early work of Shor, Aronoff, or Knill, Laflamme, several others. But the general idea is to take ideas from classical error correction, where you do redundant encoding, and you need to do this for conjugate bases, since we're using the laws of quantum mechanics. And then there are several different sort of gadgets that are used. Frequent ones are gate teleportation, where you create some entanglements and then perform some measurements and teleport a gate. Frequent use of refreshable ancilla, you need to dump entropy, so you need to have a way to reset ancilla, and you'd like to have massive parallelism. And so, the stages of quantum computing, preparation of states, unitary gates, measurement in some fixed basis. But real operations have errors and take time. There's preparation, gate errors. There's single qubit, 2-qubit gate errors, measurement gate errors. And then these all have associated execution times to them. And so the bigger the computation, the more accuracy we need. And we also need to account for the fact that if we have faulty operations in our gates, that those faults can spread. And so you want a way to control this. And so the general strategy is to redundify. So, just for a classical redundancy code, quantum state A0 plus B1 can get redundified to A000 plus B111. And then you can introduce some ancilla that you prepared and some fiducial zero states, measure a syndrome, and perform a correction. And actually, you can get rid of quantum error correction doesn't actually require measurement. You can do measurement-free quantum error correction using coherent feedback. So that measurement is not a requirement, but you do need to have lots of fresh ancilla. And there are various ways to make the entire process fault tolerant so that you can enable arbitrarily long computation. And maybe the easiest understood is to use concatenation, where you replace physical zero with logical encoded zeros at many levels of concatenation. And then there's a threshold error below which you can do arbitrarily long computation. So just a flash primer on quantum error correction. But just to note that the threshold that you get depends upon the code you're using, the circuit design, and the error model. And so for stabilizer codes, these are the most frequently studied ones. You start off just with some notation. There's the poly group on n qubits, which is just the n-fold tensor products of the poly operators with some phases plus or minus I, plus or minus 1. And then we say that a stabilizer for a state is a set of elements in this poly group that return +1 acting on the state psi. So this is an abelian subgroup of the poly group that doesn't contain minus the identity. So for example, the state, this GHZ state has a stabilizer consisting of Z1, Z2, Z2, Z3, and X1, X2, X3. And a stabilizer code is a set of states with a common stabilizer group. And so we say that you have an NKD stabilizer code, which uses n physical qubits to encode k logical qubits, where k is n minus the number of independent stabilizers for that state or code. And d is the distance, which is the minimum number of non-identity terms in a logical operator. So the code here can correct any error that affects fewer than d/2 qubits. And there's a long history of looking at these stabilizer codes. So one of the most common ones studied is the Steen code, which uses 7 physical qubits for 1 logical qubit with a distance 3. So it has these 6 stabilizers, which gives you one qubit degree of freedom, which is a logical qubit. And the logical operators can be represented as 7-fold products of X or Z. But a logical operator times a stabilizer is also a logical operator. So the distance here, the minimum sized logical operator has distance 3. So it can correct 1 error. And then people have looked at these for quite a long time now. There's the well-known surface code, which is the stabilizer code, where the stabilizers have this nice geometrically local form. Here there's this is a 2D lattice of qubits, and the blue stabilizer would be products of Z's just along that little cross shape, and the red one would be products of X's. And these string operators here correspond to logical Z's or logical X's, depending whether they're red or blue. So for a toric code, you get 2 logical qubits, and the logical operator is represented by these strings. The strings intersect at 1 point, and so that forms a representation of SU2. You get 2 qubits. More recently, people have been looking at LDPC codes, low density parity check codes, where your stabilizers also have low weight, but they may not be geometrically local. So here's an example, something called a hypergraph product code, where the stabilizers have some longer arms here, a little more spread out. The logical operators aren't full strings, but they're horizontal and vertical operators with some missing qubits associated with them. And you can store more qubits in this code, but you don't get a distance as high as the surface code, but you can still get high distances. Other examples are holographic codes. These would be high density parity check codes. So for example, a stabilizer for the center qubit of this holographic code has support on this entire green region. So the physical qubits are on the boundary of this Macquarie disk, and the stabilizers for logical qubits represented further out in the bulk here have smaller support. So you can get kinds of codes where the weights of the stabilizers vary depending upon the logical qubit you're looking at. So these codes have been studied quite a bit. But those aren't the only things to look at. So one option is to look at other subspaces of the Hilbert space of n qubits. So we could choose a code based on symmetry. Here, like rotational symmetry. So if we consider n spin half particles with collective angular momentum j equal n over 2, then there is a basis that spans this space that's often referred to as the Dicke basis. So it's the set of states where you have a label here. N refers to the total number of physical qubits, and the label 0 refers to the Hamming weight. So it's permutation symmetric states, evenly weighted sums over states with the same Hamming weight. So these codes, the permutation invariant codes are subspaces of this maximally symmetric space. They're not stabilizer codes. They are, in fact, non-additive codes. Right. So let's just look at an example of one of these. These codes were first introduced by Mary Beth Ruskay back in the early 2000s. And there's been some work since then. Just one of the examples here was studied by Yingkai Ouyang. And these are called GNU codes. That's the GNU symbol from LaTeX. Here, if it's just a logical qubit, then you can write the GNU code words as some weighted sums over these Dicke states. So the n for the Dicke states is the g, n, u. So it's a product of these three parameters, g, n, and u. And then the Hamming weight here is g times k. So you fix g, n, and u, and then you sum over the Hamming weight according to either the k is even or k is odd. And you see these have these binomial weights. So the parameters that go into the definition of this code are a bit flip distance. So that'll be, remember, the distance is basically twice the number of errors you can correct. So this would be twice the number of bit flip errors you can correct. There's little n, the phase flip distance. And there's this parameter u, which is a scaling parameter. And then the total number of qubits, capital N, is the product g times n times u. And so these parameters are adjustable depending upon what's relevant for the noise model of your system. So if you have a biased noise model where z errors are more likely, then for a fixed number of qubits, you could increase little n and decrease little g. And yeah, so let's just get a little visualization here of these code words. So for 483 qubits, the amplitudes of these code words are binomially distributed. So let's say the 0 is given by these red amplitudes. So I'm just plotting the amplitude versus the weight on the Dicke space. So the red ones are like the 0, the blue amplitudes refer to the logical 1. And the separation between these two peaks here is given by this bit flip distance parameter g. So maybe you've seen binomial codes before. These are frequently looked at in terms of encoding in continuous variable degrees of freedom. Also, if you've seen GKP codes, you know that when you make them physical with some finite amount of squeezing, that you tend to get these things that have this binomial distribution. So it's somewhat reminiscent of those codes. The logical operators here, well, the logical poly operators have they're transversal, but they're not necessarily Clifford. So the logical X is just flipping every qubit, it's just a product of X's. But the logical Z is actually a product of Z rotations by an angle pi over 2G.
What is the role of U? Is it to change the distance?
U is just this parameter so that your number of physical qubits is equal to the product of G and U. So you can
So like why not take it 1? Then it's going to be fewer qubits.
Yeah, so well, yeah, so let's see. So I think if you have U too small, like we're using yeah, I think you I'll have to get back to you on that. Yeah, I can't quite remember. Right. So yeah, why would you use one of these codes? Well, the encoding and decoding can be easier since the operations you do don't require addressability of the physical qubits. You're working with everything is permutation invariant, so you can use global pulses, which can be easier in some implementations. Also, they can correct for deletion errors. So deletion errors are just erasure errors, but at unknown locations. And we're well aware of stabilizer codes which can correct for erasure errors. And some of them have very high thresholds, like the surface code has a threshold of 50% for erasure errors. But if you don't know where the erasures are, it's difficult in stabilizer codes to correct for that. And deletion errors can occur in physical systems. For example, if you're encoding in photons, deletions are just erasures. You just lose your photons. And you might not know which ones were lost. There can also be situations where erasure errors dominate, but it can be difficult it will require additional resources to determine where the erasure occurred. So for example, in the Rydberg atom registers, it's been estimated that you can convert up to 98% of errors to leakage errors. This is basically because one of the dominant sources of errors is spontaneous emission from excited states, and these can go to subspaces orthogonal to your qubit subspace. But to work out when a qubit has actually experienced that leakage, you need to spend additional time probing that atom to see whether it is fluorescing on a transition that couples that leaked subspace to excited states, and that takes extra time as well as resolution with detectors. So it would be an easier assumption to say, well, let's just treat that as a deletion error. And so these permutation codes can deal with that. Because they're permutation invariant, you don't care where the erasure occurred. And also, unlike stabilizer codes, these codes can perform gates outside the Clifford hierarchy. So the Clifford hierarchy is just a stratification of unitaries according to their action under conjugation. So the first level is the Clifford hierarchy is the poly group. The second level is a set of unitaries which map the poly group to itself under conjugation. So that includes the Clifford group, such as the C0 and the Hadamard, as well as the polys. The third level is the map which maps poly to the Clifford group. And that includes like the T gate and the controlled Z gate and so forth. But the gates you get from these, the Clifford hierarchy have a certain structure. Particularly, you get things like Z rotation errors that look like rotations by pi over 2 to the k. But it's possible to go beyond that. Yeah.
So can we go back?
Yeah.
What did you mean by the first dash global pulses?
Oh, yeah, just that your operations can be acting the same on all the qubits. So because you're in a rotationally symmetric space, then your operations are just global rotations.
Can I say something? Actually, I think that the U controls how many erasure errors you can correct. Sorry, I'm outside. Sometimes I'm not to speak too much, but I think that's why you don't want the U to be too small, Mars.
Yes, yes, absolutely. Yes, you're correct. That's right. Yeah. Yeah, thank you. Right, so this is just to go through like a construction of one of these codes, which has transversal Clifford gates. There was this code proposed by Jonathan Gross 3 years ago. And the idea is that you want to have your Clifford operations on the code be transversal. So just be these global operations. And well, so a way to look at that is you can look at the stabilizer states for a single qubit. So these are the plus and minus eigenstates of X, Y, and Z. So it's these 6 states with, represented on the block sphere. And so the operations which permute the labels on these states can be thought of as, well, as actually rotations of a cube, where you associate each stabilizer states with a face of a cube. And so these symmetry operations for the single qubit Cliffords are like the symmetry group of the binary octahedral group. And here are all the elements of this group written in terms of the Clifford gates, Hadamard, the phase gate, and poly X, poly Z, and poly Y. So if you want to have this code have transversal Cliffords, then you can define a projector onto the irreps of this group, where we just sum over the group elements with characters for that group, and then the DJG is going to correspond to the J will be the irrep for that group element. And if we want to encode this into a permutation invariant code, then you want to basically look at the irrep, which is for SU2 n over 2. And then this will give you a projection onto the Z operator for that encoded qubit, which will have these Clifford gates as SU2 gates. So it'll just be collective rotations. So yeah, so the transversal gates you get here are H, S, X, and Z, single qubits. And you can also get a 2-qubit Clifford gate, which is generated by collective rotations of, say, logical qubit B, collective rotation of logical qubit A, and then a coupling between A and B of the form JZ, JZ. So, so in many phys systems, that kind of interaction can be designed. And so this gives you a way to perform these Clifford gates transversally. And just for a look, the logical code words here have, well, they're just superpositions of these Dicke states. And, the logical 0 is related to the logical 1 by a collective bit flip. So e to the I pi j x maps you from logical 0 to logical 1. And there are other permutation invariant codes. So there's this 7-qubit code which has transversal z rotations on the logical space by angles 2 pi over 5. So notably, this is outside the Clifford hierarchy. And these codes are fairly simple. They're just superpositions of 2 Dicke states. There's an 11-qubit PI code which has a transversal T gate. So this might be useful for certain compilation. And then how would you make use of these? Well, what you might want to have is a scenario where you're doing error correction and quantum memory storage in a stabilizer code. And then when you want to do a non-Clifford gate, you basically switch to the other code, the PI code, do your non-Clifford gate, and then switch back. So one way to do this could be, for example, let's say you had a 7-qubit Steen code, and you wanted to do a non-Clifford gate on that. Well, then you could prepare one of these 7-qubit PI codes in a logical 0, do a C0, well, a sequence of 2 C0s on them, do the transversal Z rotation on the permutation invariant code, and then do the X2 C0s, which basically just swaps it back. So that'll give you the non-Clifford gates on the encoded information back in the Steen code. Of course, you have to figure out a way to do these C0 gates in a way that's fault tolerant. Yeah, that's something we're actually, Yingkai and I are looking at right now, how to do that in a way that at least doesn't cause a spread of errors during the gate. So you might wonder, well, how is this any better than just using other methods for code switching? Like, people talk about switching from surface codes to Reed-Muller codes or other codes where you have transversal T gates. Well, there's a couple reasons. One, it might be useful in the compilation of a quantum algorithm to, rather than always describe things in terms of T gates, doing things in terms of gates with other rotational parameters. So you might get some speed up from that. The other thing is there's been some recent work which has shown that the overhead for approximating unitaries in SU2 using the Kitaev-Solovay decomposition can be reduced by, rather than working with, say, T gates, working with another non-Clifford gate, which is outside the Clifford hierarchy. So we don't know yet whether there is a PI code which will allow you to do that transversally, but it is good motivation to look for one. Okay, so the actual process of error correction with these codes is still, I would say, early, but I'll just show you some work that Yingkai and I have been doing. So, errors can take you outside the symmetric space. So we need a way to characterize how those errors act and how we might be able to do correction. All right, well, since we're sort of motivated by the symmetry of the problem, then let's just analyze the action of errors in a similar representation. So we can use the Schur-Weil duality to rewrite the Hilbert space for n qubits. in terms of a direct sum over Young diagrams, where a Young diagram is just, for SU2, it's just a diagram with 2 rows. There's a top row with R1 boxes and a bottom row with R2 boxes, so that R1 plus R2 is equal to the number of qubits. And this shape is determined by the value of the, well, the eigenvalue of the operator J squared. So if you just have a single row, then J has value n over 2. And if you have, like if there were just 2 qubits, a vertical column with 2 boxes would be a J equals 0 irrad. And if you had multiple rows, then the amount of, basically the thing that left dangling over tells you what the residual J is. And then within the Young diagram space, there's a standard Young tableau, which is an ordering of numbers inside these boxes, so that they are non-decreasing as you go right and go down. And the numbers you put into those boxes, which specifies the Young tableau, is actually given by the eigenvalues of J squared for different subsets of qubits. So like the first qubit, the first 2 qubits, the first 3 qubits, up to the first n minus 1 qubits. And so those observables tell you what Young tableau you're in. And then finally, there's a semi-standard Young tableau, which is an ordering of these boxes with 1s and 2s. And that ordering is determined by the eigenvalue of the collective JZ operator. So for error correction, what you can do is perform a measurement of the total angular momentum on subsets of spins to project onto a Young diagram and a semi-standard Young tableau. And for a code like this GNU code, what we like to have is a way to measure the JZ operator modulo the distance of the bit flip distance here. So we want a way to measure whether you had a shift in your code, but without acquiring information about this quantum state. So if we had a way to do this modular measurement, then we would be able to achieve that. This is kind of very similar to how you want to do measurements on GKP codes, where you want to measure displacements modulo root pi over 2. And then after you perform these measurements, you'd want to have a way to correct. And there are different options, but one way you can do this is via teleportation. And I think I have a slide here. Yes, so one way you could do a correction is by teleportation. So let's say you had your register, row B, which had experienced some errors. Then you could prepare another logical state in the plus state for PI code, perform something we call a C naught, followed by one of these modular measurements of JZ, and then based upon the outcome of that, perform a controlled logical X operator. The logical X operator is just a transversal bit flip, so that's not hard to do. This C naught here, what it actually does is it applies the identity operation if the control is in the logical 0, and if the control is logical 1, then it applies what we call an X sure operation, which basically maps you from an M state according to the space you read out from your measurements of the J squared operators into the negative of that M state. So it's like a flip, but possibly not in the symmetric space. And okay, there's a way to do this C naught using geometric phase gates, which I'll get to. How long am I going actually today? Is it to the 45 or
50 or so, it's fine, we started a bit late.
so? Okay, great. Yeah, so there's a way to do this C naught operation using geometric phase gates, which I'll get to a little bit later. But the general idea is that if you can couple this ancillary register qubit to a bosonic mode with a dispersive coupling so that it couples to the number operator of the bosonic mode dependent on the Hamming weight of that state. And then you can realize this controlled X operation by doing displacements on the mode as well as evolving according to this interaction for a time G prime times T equals pi. And so this gives you a way to do this kind of teleportation and correction. Yes. So I just want to also mention that to do these measurements of the J squared operators and the modular measurement of JZ, you can get some help from a boson. So let's say you want to measure a total angular momentum. I'm not saying that this is the most efficient way to do it, but one way you can do it is you could couple your spins to a bosonic mode, and with an interaction that looks like an X quadrature for the mode coupled to J squared for the spins. And then if you evolve this, what will happen is the mode will experience a displacement that's proportional to the eigenvalue of J squared. And so if you started, say, in the vacuum state, then that state will get displaced. This is in the rotating frame of the mode. And the different eigenspaces of J squared can be distinguished by then doing a homodyne detection on the mode. So this is a representation of the phase space for the mode, where different blobs here refer to the displacements experienced by the mode according to the value of J squared for the spins. And so if you're close to the maximally symmetric space, you're in the region where the gap between these blobs is big, because the eigenvalue is near maximal for J squared. And so you can distinguish these subspaces fairly accurately. To do the modular measurement of JZ, so this is to get a measurement of JZ modulo the bit flip distance. What you can do is to, again, make use of a coupling to a mode, but where it's a dispersive coupling. So you have a coupling that looks like A dagger A times JZ for the spins. Then if you prepare your mode in a displaced coherent state, so here's the phase space, here would be the vacuum state, you displace it, and then you evolve the system according to the dispersive interaction. What will happen is the coherent state will get rotated, and if you wait then for appropriate time, then like if you wait for time pi, if the coupling G is 8 here, then you get these distinguishable distributions for the mode. And so if you were to measure one of these, you would extract the eigenvalue of JZ modulo the G parameter here, the bit flip distance. So as long as your initial displacement is big enough, these blobs are distinguishable enough so you can perform that measurement and with high confidence know that you projected onto that eigenspace. All right, so I did want to talk a little bit about how we can apply these codes to quantum sensing. This is something that Yinkai and I have been working on. And if, I don't know how many of you are following the field of quantum sensing much, but the experimental treatment of quantum sensing, for the most part so far, has focused on sensing with non-entangled states. So just single particles, but that can, you can use lots of quantum particles to get a signal. The real advantage comes from being able to use entanglements, because you can reach a Heisenberg limited precision, which has a scaling of precision that goes like 1 over the number of systems, whereas the single particle sensing shot noise limit scales like 1 over root n. But the problem is that the same physics that makes your sensor very accurate to sensitive to signals you want to measure also makes them very susceptible to errors from signals you don't want. So the real challenge has been to find a way to do quantum sensing with entangled states that doesn't get destroyed by decoherence. So we looked at this process where you would prepare some probe state, some entangled probe state. There could be noise during this preparation. Then there's some signal accumulation, the thing you want to measure, that can have noise. And then there's the final measurement, which could also have noise. And let's have a look at this. Okay. So the general framework here is to use one of these permutation invariant GNU codes for quantum sensing. And why would you want to do this? Well, it's because if you look at, let's just look at a representation of these code words for the GNU code. So I've just drawn them so like the logical 0 and logical 1 look like they're living on planes that are perpendicular to each other. And the amplitudes of the Dicke weights are indicated here, red for 0 and blue for 1. If you let this code interact with a field you want to sense, so for example, let's say you want to measure magnetic field along the z component of a magnetic field, then that will induce a rotation that's described by a unitary e to the I theta jz. And theta is the thing you want to estimate. That's the strength of the field component. Well, what this will do is it will perform a rotation on the frame of our code. So we can now have define this 0 as a logical 0 with a theta parameter. And same thing for the logical 1. But the important thing is that this rotated frame also satisfies the Canel-Laflamme error correction criteria for any multi-qubit Pauli operator with weight less than the minimum of G or N. These are the bit flip and phase flip distances. So basically, the action of the field that we want to acquire information about preserves the error correction properties of our code. Right, so the steps then are going to be, can we prepare these code words robustly? And can we do error correction and do an inference of what the signal strength is with high fidelity? So to stick at the first part of this problem, turns out, yes, you can prepare these code words. So there's a variety of ways to do this. Here I'm just going to talk about one way that's making use of geometric phase gates. And then there's some nice work that I've been doing with Liam and Argivon on another way to do this, which is actually simpler than what I'm going to describe here. But I'll just take you through the steps of this one. The idea is to start off with a bunch of spins in a product state. and make use of geometric phase gates combined with some global rotations on the spins in order to end up with an entangled state which lives in the Dicke subspace. And in particular, it could be one of these permutation invariant code words. What are all these funny parallelograms here? These are indicating trajectories of a mode in the phase space. But first, I just want to point out that there's been quite a bit of early work on how to make Dicke states, but it's typically not easy. So there is a quantum circuit method to construct Dicke states. The best one I'm aware of so far to prepare a Dicke states on n qubits with Dicke weight W requires order n times W gates, and the best depth is W log n over W. And it does require a universal gate set and addressability of the qubits. There's other methods like adiabatic preparation, where you would start from, say, the all zero state, which would be the Dicke states with weight 0, or in the angular momentum notation, you indicate that by the JZ eigenvalue, which is minus n over 2. So there is a way you can walk amplitude from this state to higher states in the Dicke ladder, but this requires strong constraints on the detuning of your pulses, and in order to only walk one step at a time without also coupling to higher levels in this Dicke space, there's strong constraints on the adiabaticity criterion. So you have to do things very slowly, especially as the number of qubits grow. Basically, you have to break the degeneracy of the spacing of these qubits in some manner, and doing so while making sure you have high fidelity couplings just between pairs of states on that ladder becomes increasingly hard as the n grows. There's other ways where you can try to use things like dipole-dipole interactions to break the degeneracy, but this requires very special geometries in order that you don't couple the states outside your maximal symmetric space. So we want to look for something simpler here. And we looked at a situation where you have your spins coupled to a bosonic mode. It might be a cavity, for example. So it could be that you have some cavity which has some decay described by parameter kappa, and it couples to the spins by a strength G. And this could correspond to like the collective motional mode of trapped ions. Or it could be superconducting qubits that are coupled to a microwave resonator mode. Or it could be NV centers coupled to a microwave cavity, atoms and molecules coupled to an optical cavity. Or you could use Rydberg atoms that are coupled to a microwave cavity. So there's a lot of different options here, and a lot of experiments that are probing these different scenarios. The kinds of control we need are displacement operators on the mode. And we do not need direct interactions between the spins, but we will need dispersive coupling between the spins and the mode. So this forms number operator times JZ. So the principle of this geometric phase gate is it's just a walk around phase space. So if we were to think about this trajectory as indicating where the mode goes, where the mode moves in phase space, defined by the quadratures Q and P, then it involves the sequence of steps here, where you do this dispersive shift R theta JZ, where R theta JZ is just the unitary generated by exponentiation of this dispersive coupling. So effectively what it does is it performs a rotation of the spins dependent upon the number of photons or the Fock state of the mode. And then you have displacements. So dispersive shift, displacement, dispersive shift, displacement, and so forth, going around in the closed trajectory. And after you make these steps, the mode returns to its initial state, but there is a non-trivial action on the spins. And that gate looks like a unitary that's generated by a highly nonlinear operator in JZ. So it becomes disentangled from the mode, but you have this nonlinear action on the spins. And just a way to sort of visualize this, let's take a case where you have an even number of spins and you just do a trajectory that's a square in phase space. So that's equivalent to choosing, and we're going to choose this angle theta here for the rotations to be pi, and phi equals pi halves basically is telling you that you're doing a square. Well, you can look at the action of this on the Dicke states with even Hamming weight first. And for those with even Hamming weights, what happens is you just form this closed trajectory in phase space. Because W is even, then the action of this rotation is, well, you'll get a 2 pi action here. And if the weight is odd, then you get a trajectory which looks a little bit different. So the first step takes you over to the right. The second step takes you over here, the third, fourth, fifth, all the way up, and then finally you return to the origin. Now, this is a geometric phase gate, so the action is determined by the area traversed in phase space. In the case for even Hamming weight, we get an area that we could say is positive because the trajectory has this counterclockwise sense. Whereas in the case with odd Hamming weight, you're making a trajectory with a clockwise sense to the area. So the areas have different signs for these two spaces. And the net action is to give you a unitary, which is an exponential of the product of Z gates on all the spins. So this is a highly entangling gate. And for example, you could use this to generate a GHZ state in one step of this geometric phase gate. Okay, so if we know a little bit about the physics of the geometric phase gates, how are we going to use this to help us make our Dicke states, our superpositions thereof? Well, the idea is we want to bring some tools from quantum control theory. Particularly, we want to just see how we can achieve all the elements necessary to perform unitaries on this space. So the first thing we would like to have is a way to apply a phase just on one Dicke state. Well, that can be realized by taking products of these geometric phase gates where we just use a rule that because these gates commute, it's easy to analyze what gate we would need in order to get a phase occurring only on a single Dicke state. So we just make use of the sum rule for cosines, and that allows us to determine a sequence of angle parameters theta and phi, which are ingredients in our geometric phase gate, in order to obtain the phasing of a particular Dicke state with Hamming weight L by an angle lambda. And the lambda here is just determined by basically the area of these phase gates. So there's a way using n halves geometric phase gates to phase a particular Dicke state. Then an arbitrary unitary on the Dicke subspace Well, you could write it in the just eigendecomposition with eigenvalues lambda and eigenvectors lambda. But another way to write the unitary and the Dicke subspace is to use the spectral decomposition. So here above, but written in terms of a product of operations where you look at mappings from a particular Dicke state, like the zero Hamming weight Dicke state, to an eigenvector of u, phase this particular Dicke state, and then reverse that mapping. So this is just another way to write the spectral decomposition of u, but I've written it here in terms of products of state mappings and phasings. So that reduces then the problem to determining how we can do state mappings from this zero Hamming weight state, which is really just a product state of all the spins in zero, to an arbitrary Dicke state. And that mapping, it turns out, has an exact decomposition in terms of n-1 geometric phase gates. The existence of this just follows because you have enough parameters to match the dimensionality of the target space. And then you can solve for what the angles you need here are by an efficient search. So overall, this implies that the state synthesis problem using geometric phase gates has a complexity n, and then the unitary synthesis problem has a complexity 5n squared over 2. Yeah, and then you can look at the performance of this. I should get hurrying up here, but you can look at the performance of these state preparations when you include the noise relevant to the problem, which includes the cavity decay and also having dephasing. If you have cavity decay, it turns out that the cost to the process fidelity for preparing a particular Dicke state is not too bad. So the fidelity error rate, if you like, it goes like end of the quarter. So it has a rather weak scaling with the number of spins. Here, kappa is the decay rate of the cavity divided by g, which is the coupling rate to the spins. Yeah, and I won't go through this, but there's actually a faster way, which is less noisy, to get to a particular Dicke state by using amplitude amplification. And then I'll just point out one other thing. When you have dephasing acting on the spins during this process, actually, this state preparation has a built-in dynamical decoupling in it. And that's because the geometric phase gate you apply here involves these dispersive interactions at the 4 vertices of this trajectory, but in 2 of them, the signs are changed. So this changing the sign of the dispersive interaction is the same as flipping all the spins and doing the same dispersive interaction. So basically what we're doing is a bunch of gates where every other pulse, we're flipping all the spins. So this will actually tend to reduce the noise due to dephasing. So you can look at the effects of improvements of the protocol due to the fact that you have this dynamical decoupling built in. Won't go through this, but it just basically, if the rate at which you can do the pulses in your geometric phase gate are fast compared to the rate that the environment couples to your spins, then you win in terms of dynamical decoupling. And so the final performance you get for this kind of thing is, like here we just looked at the case of 70 spins. And if we look at the fidelity, or this is actually a plot of infidelity to reach a particular target state, which is the state in the middle of the Dicke ladder, versus the cavity decay rate or the mode decay rate, then you get fidelity errors that are actually quite reasonable. Like the capital over G here in many systems can be 10 to the minus 6 or better. So you get, quite decent fidelities, even for these finite decay rates. And the numbers here refer to the ratio of the cutoff frequency of the coupling between the modes in the environment that gives rise to dephasing and the fundamental interaction strength between the spins and the mode. So if you look at if you were to use this state for quantum sensing, then we have the shot noise limit, which is what you can get just using independent quantum systems without any entanglement. And there's the Kramer-Rao bound on the precision of estimation, which is the best you could get. And you see that we're certainly getting improvements over the shot noise limit. This is for 70 spins. So it shows some promise. And well, yeah, I don't have time to go through it, but in fact, you can incorporate this this error correction with the permutation invariant code together with a sensing protocol to actually see an improvements of your quantum Fisher information, which is telling you basically how well you're able to extract information about a signal. You could get an improvement by using error correction as opposed to not. And so it turns out then if you use a nested protocol where you acquire some information about your signal, perform some error correction, update how you prepare the state, acquire some more information, and do further rounds of error correction, that you can get improvements over just the shot noise limit, which approaches the Heisenberg limit, but doesn't quite reach there. Turns out our protocol is using a finite number of rounds of error correction, as opposed to taking a limit where you'd have arbitrarily fast error correction acting on your system. So, but yeah. Okay, so maybe I'll just leave it there. Just to summarize, we can use geometric control to prepare entangled states for sensing. And we can also use it for preparing permutation invariant codes. And the error correction being incorporated into the scheme in a useful way that maintains quantum advantage. The control is not too heinous. It does require having a bosonic mode around, but the operations don't require addressability, and some of the assumptions about the errors seem to be played out in experiments. But there's several open questions. One is, how can we adapt this sensing protocol to cases where the permutation symmetry is broken? So where your signal may not be acting the same on all the qubits. And then the other open questions is, can we find a fault-tolerant way to do code switching from stabilizer codes to permutation invariant codes and back? So some of these schemes I mentioned for doing the code switching with controlled NOT gates, there doesn't seem to be a direct transversal way to do it with C-NOT gates, but there is a way to do it assisted by cavity mode. But whether we can make that fault tolerance with a reasonable error model is not totally clear yet. Okay, thanks.